Hello everyone, thank you for listening to my presentation. My name is Nooshin Yousefi and I'm PhD student at Rutgers University. I'm working with Professor David Coit. The title of my presentation today is Dynamic Maintenance Modeling for Degrading Systems with Multiple Repairable Components. Today is very important for us to have products with high reliability, longer lifetime, and higher performance. There are lots of accidents reported in the history of different industries such as railroad, aircraft, or bridges. And the main reason of this failure is the poor quality of their material or the low reliability of their system. One way that we can increase the reliability of different systems is by providing an appropriate maintenance model. But before that, we need to understand our system and we need to know how is the failure behavior of our system. There are two main reasons for the failure of the systems, like deteriorating process such as aging, wearing, corrosion, and environmental factors such as temperature, humidity, and wind speed. This photo shows a rebar that is located inside the concrete, and this rebar degrades over time and it reacts with different environmental factor, and it occupies a space 6 times of a new rebar. And this increase in the size of the rebar caused some crack in the reinforce and eventually caused the failure of the system. So the main step to formulating the failure behavior of our system is by having an appropriate model for the degradation process of the component inside the system. There are different degradation models in the literature, but here I used gamma process for the degradation of all the component inside the system, because gamma process is an appropriate process for systems or component that has monotonically increasing degradation paths. In gamma process, the degradation level between two time points follows gamma distribution with some shape and scale parameter. So in this research, I consider two competing failure processes. One of them is related to the degradation, and one of them is about the shock process. So I assume that each component degrades over time, and whenever one shock coming to our system, it has a damage on the degradation of each component. And whenever the cumulative degradation process of each component is above some threshold, we call it soft failure happen. And also we consider that each shock has a magnitude, and whenever the magnitude of any shock is above a predefined threshold, we call it hard failure threshold. So in this study, I consider a gamma process for the pure degradation of the components, and I assume that the shock damage follows normal distribution. I also assume that the shock coming to our system based on Poisson distribution and their magnitude follows normal distribution. So this is about the competing failure processes for all the components inside the system. So for the maintenance problem, I want to have another threshold called unconditioned threshold to replace the component before failure happens. So in this paper, I want to have a dynamic maintenance model that by considering the initial degradation of all the component at any inspection time, we want to find what is the next inspection time and what is the next unconditioned threshold for all the component inside the system. So the main difference between static models and dynamic models is in a static maintenance model, we have some fixed rule for the whole maintenance contract. But in dynamic maintenance model, we update the decision maintenance such as inspection time or the maintenance threshold based on the current degradation of the components. So in this study, I want to find how I can find the next inspection time and the unconditioned threshold for all the component, considering the initial age of component at each inspection time. So before everything, I need to formulate a maintenance cost rate. So in this case, I consider different costs for this system: inspection cost, setup cost, replacement cost, and downtime cost. So here, at any inspection time, we may have more than one component above their unconditioned threshold. So it means we have for example, K components that they need replacement. So for all of these K components, we have one shared setup cost and we have K replacement cost. And also we need to calculate what is the probability that we have K component needs replacement. In this case, we need to find what is the probability that each component has the degradation between unconditioned threshold and failure threshold. And by having a binary variable 0 and 1 for components which needs replacement, we can calculate this probability. And also for downtime costs, we need to find what is the expected time that the system is down. So in this case, we don't have any continuous monitoring. So it means we may notice the failure at each inspection time. So if the system fails within an interval, so from the failure time until the end of the inspection, we have a time that the system is down. So we need to find what is this expected time. So in this case, I need to use the probability density function of the failure time when all the component starts from initial age and their degradation is above H1. And then by having this maintenance cost rate as the objective function of the optimization problem, I can solve an optimization problem and then find the maintenance decisions such as inspection time and unconditioned threshold for all the components inside the system. So here, the idea is whenever, so the maintenance team can go to the field, they can measure the degradation of all the components inside the system. They can feed this information into the optimization problem, and then by solving the optimization problem, they can find the maintenance decisions such as thresholds and the next inspection time. But the problem here, the maintenance optimization problem is a very complex problem, and solving this complex problem takes a very long time, and it's not beneficial for the maintenance team to wait in the field until the optimization is solved and then they can find the maintenance decisions. So in this case, I want to have an alternative way to find these maintenance decisions very fast and in a very quick time. So in this case, I want to have a neural network and then train this neural network for the maintenance team to find the maintenance decisions very fast. So in order to train this neural network, I need a data set. So I simulated different scenarios for the degradation of the component inside the system, and then usually by solving the optimization problem, I found the optimal inspection time and the thresholds. And then by considering all of this information as the data set for training the neural network, we can have a trained neural network for the maintenance team, and they can measure the degradation of all the components. They can feed it into this neural network and they can find the maintenance decisions. So in this case, I use 70% of my data as the training set and 30% for the testing set. And I also use coefficient of determination R-squared to find how close is the result of the neural network and the result of the optimization problem. So as you can see here, the red dot is for testing set and the blue dot is for training set. And for both of them, we have a high R-square, which is very close to 1. And we can say that the predicted inspection time from the neural network is very close to the inspection time after solving the optimization problem. I also calculated R-square for different thresholds. For example, if you have two components inside the system, for both of them, for the thresholds of both of them, we can have, as you can see here, the R-square is a high number. So here we can conclude that the result of the neural network is very close to the result of optimization problem. Or in other words, I can conclude that neural network is a good alternative method for the maintenance problem. So I also here I did one analysis for the optimal number of neurons in each layer of the neural network. I consider two error measurement, MSE and average RMSE. And as you can see here, by increasing the number of neurons, the error for training set decreasing, but at some point the error for test increased. So in this case, I can find what is the optimal number of neurons for this neural network. But I should mention here, this optimal, it depends on the systems. So for different systems, the maintenance team need to find their own optimal number of neurons for their neural network. I did one simulation run here to show how we can use this neural network as a decision-making tool. So at the beginning, the system is new, all the components are new, and their current degradation is 0. So we feed 0 into the trained neural network, and then we can find the next inspection time and unconditioned thresholds. And then after this amount of time, again, we need to measure the degradation of the components. So if this degradation is not above the maintenance threshold coming from the previous step, so we don't need to do anything. We need to just feed it into the trained neural network and then find the maintenance decisions. But here, for example, in step 3, you can see that the degradation level of component 1 is greater than the unconditioned threshold from coming from step 2. So it means we need to replace component 1, and then we feed 0 into the neural network and then continue the process and finding the maintenance decisions. I also did another simulation run, and here, as you can see, so in the first step everything is the same, but in the second step, after the same amount of time, the degradation of the components are completely different. And this is because the gamma process is a stochastic degradation process, and at each simulation run we may have different degradation level. And then also I can conclude that this neural network can be used for any kind of system, and the initial age can be any number, and based on that initial age or the current degradation, we can find the optimal maintenance decisions based on the trained neural network. I also showed the result of the first simulation run here in this plot. As you can see here, from the beginning, everything is new. Both of the components have the degradation equal to 0. And then by feeding into the neural network, we can find the next inspection time, and we can measure the degradation of both of them after this amount of time, compare it to the unconditioned threshold from the previous step. If it's not above that, as you can see here in the first step, it's not above the unconditioned threshold, so we don't need to do anything. But in the second step, so one of them has the degradation level greater than the unconditioned threshold, so we need to replace it and then feed 0 into the neural network. So as a conclusion here in this paper, I propose the dynamic maintenance model for a system with multiple repairable components, and when each of them is subject to degradation and random shock. I developed a system reliability and formulated the maintenance cost rate considering the initial age of the components. And then I also proposed the alternative neural network for the maintenance optimization problem, and I did some analysis for neural network. And at the beginning, I should mention that using this proposed model, we can have a dynamic maintenance model that at any time, based on the initial age of the component, we can find the next maintenance decisions, such as inspection time and unconditioned thresholds. Thank you for listening, and I would be happy to answer your question.